All right, so now I want to talk about oxidation and reduction reactions. So in oxidation reduction reactions, there's a movement of electrons from one reactant to the other. So one of the reactants has something being oxidized or losing electrons. Another one of the reactants has something being reduced or gaining electrons. The way to remember oxidation reduction is Leo-Gur. Leo loses electrons oxidized, loses electrons oxidized. Leo gains electrons reduced. Okay, so whatever's losing electrons is being oxidized, whatever's gaining electrons is being reduced. Now we have some rules about assigning oxidation numbers, and in our textbook, it's on page 160. So on page 160, there's a list of rules. Rule number 1, for an atom in its elemental form, the oxidation number is 0. Okay, so oxidation number is similar to charge, but there is a difference. So oxidation number for anything in its naturally occurring state. So all of the Hofbrinkel ones, O2, H2, F2, and so on. In those naturally occurring diatomic molecules, the oxidation number of the H or the O or the F is 0. Okay, so all of the Hofbrinkel. So in that case, Cl would be oxidation number of 0. H in that would be oxidation number of 0. Also, for all metals, when they are not ions, so they're just in their naturally occurring state, like calcium or lead or whatever, if it's in its naturally occurring state, it has an oxidation number of 0. Okay, anything in its naturally occurring state. For sulfur, sulfur naturally exists as S8, phosphorus naturally exists as P4. In those, the oxidation number is 0. Rule number 2, for a monatomic ion, the oxidation number is the ion charge. So that means for the ions that we've already talked about, so we've already talked about that as ions, all the alkali metals are +1. Group 1 is +1. All the alkaline earth metals, group 2, are +2. The halogens as ions are -1. Well, those are their oxidation numbers too when they're in a compound or as an ion singly. So like in NaCl, the Na is +1 charge, that's also its oxidation number. The Cl is -1 charge, that's also its oxidation number. Okay, so we've had that before. For then the sum, rule number 3, the sum of the sum of the oxidation number values for atoms in a molecule or formula unit of a compound equals 0. So we have also done that before when we're figuring out charge or formula. We know that they have to add up to 0. So for instance, in H2SO4, all those oxidation numbers would have to add up to equal 0. Okay, in HCl, the oxidation numbers equal 0. All right. So then for a polyatomic ion, the oxidation numbers have to add up to equal the charge. So if we have SO4 -2, that means that those oxidation numbers are going to add up to -2. Okay, so for example, oxygen. Oxygen is almost always -2. So if oxygen is -2 in this compound or in this ion, and there's 4 of them, 4 times -2 is -8. And then that tells us that something for the sulfur plus -8 equals -2 overall. So in this case, the sulfur in that compound has to be +6. Okay, so sulfur is +6 in there because the oxygen's -2, and they have to add up to be -2. 2 overall. All right. So it's like a little math problem sometimes to figure out what the oxidation number of things like sulfur, nitrogen, chlorine in compounds, because even though we said as ions, chlorine is -1, sulfur is -2, nitrogen is -3 as ions, when they're in covalent compounds, their oxidation number is not going to be the same as their ion charge. So that's why sulfur is +6 here. If we looked at NO2, we know oxygen is mostly -2. So -2 times 2 is -4. That nitrogen has to make it add up to 0 because it's a compound. So that means the nitrogen is +4. Versus in NO3, 3 oxygens make -6. So that means this nitrogen is +6. So that's why there's lots of different oxidation numbers for the nonmetals when they're in covalent compounds. So that's what we're following. So a few more rules on page 160. We've kind of already said. So group 1 is always +1, no exceptions. Group 2 metals, the alkaline earth metals, always +2, no exceptions. Hydrogen is +1 when it's with a nonmetal and -1 when it's with a metal. Okay, so hydrogen is +1 with metals. I might have just said that backwards, but it's +1 with metals and -1 when it's with nonmetals. I just said that backwards. Okay, so back up. Sorry. It's +1 when it's with nonmetals. Yeah, end of the day, a little tired. +1 with nonmetals, -1 with metals. And if you remember, metals are always going to be positively charged. So when hydrogen's with a metal, it's going to have to be the minus charge thing. So for instance, in HCl, chlorine's -1, hydrogen's +1. But in sodium hydride, NaH, sodium has to be +1. They have to add up to 0, so that makes the hydrogen -1. Okay, so hydrogen is +1 with nonmetals, -1 with metals. Make sure you get that straight. Sorry, I said it backwards there. All right, number 4, fluorine is always -1. Okay, so that one is a set. So fluorine is -1 always for oxidation number. Oxygen most of the time is -2, but when it's in a peroxide, oxygen is -1. So there aren't very many peroxides. Some of the alkali metals and hydrogen make peroxide. There's a few other alkaline earth metal that could be peroxide, but for the most part, oxygen is -2. And you'll know if it is with something that can't be any other charge, like an alkaline metal or alkaline earth metal, you'll be able to figure out that the oxygen is -1. So for example, in hydrogen peroxide, which is H2O2, we just said hydrogen is +1 with nonmetals. So if it's +1 and there's 2 of them, that's +2, which means the oxygens total can only be -2, and there's 2 oxygens, so each oxygen can only be -1. All right, so those rules are on page 160, and you need to know those rules. Okay, so look those over. The last one on there is for the halogens for group 7A or group 17. It's -1 when they're combined with metals. So we're talking about chlorine, fluorine, bromine. They're -1 with metals, but with nonmetals, they can vary. Okay. Especially with oxygen. So with other nonmetals, they're usually -1, but with oxygen, they're going to be all different oxidation numbers. Okay, so In this equation, it says assign oxidation numbers to all the elements. All right, so if it's naturally occurring Hofbrinkel, it's 0. So the hydrogen in this H2 is 0. The chlorine in this H2 is 0. Okay, but in this compound, then hydrogen's +1 and chlorine's -1. So what's happening? The hydrogen is going from 0 to +1. So it had to have lost an electron to get more positive. So hydrogen lost an electron. So it's oxidized. Loses electrons, oxidized. If it's getting more positive, it means it's losing a negatively charged electron. Chlorine, on the other hand, in this equation, on the reactant side is 0, on the product side is -1, so it gains an electron. So it's being reduced. So if the charge is getting more negative, it's being reduced. If the charge is getting more positive, it's getting, or the oxidation number is getting more positive, it's being oxidized. How about here? We look at the oxygen is -2, so that lead is +2. In here, again, oxygen -2, so the carbon's +2. Over here, lead's by itself as a solid metal, so it's 0. And here, now it's CO2, oxygen is still -2, so 2 of them are -4. That makes the carbon +4. So the lead starts off as +2, but is going to 0. So is it getting more positive? No, it's getting less positive or more negative. So it had to be reduced. It's gaining electrons to get less positive. Whereas the carbon is +2 on the reactant side, but it's +4 on the product side. So it's being oxidized because it's getting more positive. Okay, so this one was getting less positive or more negative. This one's getting more positive, or less positive, more negative. So this one's getting more positive. So it's oxidized. So it lost negatively charged electrons to become more positive. So lead is being reduced, Pb. Carbon is being oxidized. Oxygen staying the same. In oxidation reduction reactions, you'll always have, if you have one thing being oxidized, something else has to be being reduced. They always have to go together. But then you can have other atoms in the equation that aren't changing oxidation numbers, so they're just staying the same. So in this one, oxygen's staying the same. Okay, but you can't have one thing being oxidized and nothing being reduced. They always go together. If one thing's giving up electrons, the other thing has to be gaining electrons. Then we have something called oxidizing agent, and that's the species doing the oxidizing, or reducing agent is the species doing the reducing. So these are going to be reactants, and they're going to contain the opposite, basically, of what they're doing. So the species doing the oxidizing contains the element being reduced. Remember, reduced means that it is gaining electrons. So it's oxidizing something else to gain those electrons. It's oxidizing, making something else lose electrons for it to gain electrons. If it's reducing agent, it's reducing something else, which means it's giving electrons to something else. So that means it contains something that's losing electrons. So you have to think that through, get that straight. It's a little bit confusing. All right. The oxidizing agent contains something being reduced. The reducing agent contains something being oxidized. And they're always both reactants. So when we look up here and say that carbon is being oxidized in this reaction, that means the CO2 is the reducing agent. It contains carbon that's being oxidized. So the thing that the carbon is in on the reactant side is the reducing agent. Okay, so that would be the CO. Then the oxidizing agent contains the thing being reduced. So we said lead was being reduced. So PbO contains the lead that's being reduced. So it is the oxidizing agent. So it's definitely kind of backwards. You have to think that through. The oxidizing agent contains the substance being reduced. The reducing agent contains the substance being oxidized. So let's see in this one. Again, you go through and figure out what the charge of everything is on the reactant side and what it is on the product side. The ones that have changed in, I keep saying charge, but it's oxidation number. The ones that have changed are either being oxidized or reduced. If they're getting more positive, they've lost electrons. If they're getting more negative, they've gained electrons. And then losing electrons oxidized, gaining electrons reduced. All right, so here we go. According to the rules, solid metals, not in a compound, have an oxidation number of 0. That's how they naturally occur. In a compound with oxygen, almost all the time, oxygen's going to be -2. So 4 of them is -8. So our oxygen is -2 here. Hydrogen is with all nonmetals, so it's +1. And then if that's +1, that's a total of 2. This is -8, so that means the sulfur has to be +6 because they have to add up to 0. Okay, you can write it off to the side if you have trouble seeing that. If the oxygen's -8 and the hydrogens together are +2 total, then the sulfur has to be +6 because 6 + 2, and then that's +8 with your -8 from your oxygens makes 0. On the other side, we have hydrogen here that's in Hofbrinkel, so that means its oxidation number is 0. In this compound, again, we still have sulfate, so that didn't change. The oxygen total is -8, so each oxygen is -2. And then in sulfate, the sulfur still stays the same. It's +6 because in sulfate, it's SO4 -2. So if the oxygen total is -8 and they add up to be -2, then the sulfur has to be +6. So when I have a polyatomic ion, I kind of like to take the polyatomic ions separately and make them add up to the charge to figure out what everything is. So in sulfate, sulfur's +6, the oxygen's -2. Aluminum is always +3, so that is one that doesn't change. Aluminum in compounds is always +3. So what happened? So we have our aluminum on the reactant side was 0, and on the product side, it's +3. Okay, and let me erase this. What else changed? So the oxygen didn't change, the sulfur didn't change, but the hydrogen changed. So the hydrogen on the reactant side is +1, on the product side is 0. So the aluminum's getting more positive. That means it lost electrons. So it is oxidized, aluminum. Hydrogen's going from +1 to 0, so it's getting less positive, so it gained an electron. It's reduced. Now, which one is the oxidizing agent? Again, you have to remember the oxidizing agent is the reactant containing the substance being reduced. So here is the substance containing the element being reduced. So H2SO4 is the oxidizing agent. What's the reducing agent? It's the reactant containing the substance being oxidized. And what is that? That's aluminum. Okay, it's just by itself. So aluminum is the reducing agent because it's being oxidized. H2SO4 is the oxidizing agent because it's the reactant containing the element being reduced. This is oxidation reduction. All the other types of reactions besides double replacement have oxidation reduction going on. So single replacements, synthesis or combination, combustion, and decomposition. All four of those have oxidation reduction going on. And you will be able to see that something is losing electrons and something else is gaining electrons in all of those types. That's why you can't just look at the charge on the reactant side and it's not going to be the same on the product side for some of the elements. Unlike double replacement, in double replacement, there is no oxidation reduction. And so whatever the charges are on the reactant side, those substances have the same charge, those elements have the same oxidation number or charge on the product side. Okay, so double replacement, no oxidation reduction, but all the other kinds of reactions have oxidation reduction.